Krishna's classroom. In the last lecture, we looked at the holders inequality. Which in a way generalizes the following relation, namely the inner product of x, y, where x and y are vectors in a vector space, is less than or equal to the length of x That's the generalization that you prove in the holders inequality. Or in short, you take the problem to R2 and R3 and try to understand it. Simply says cos theta is an equal. Now we look at another inequality, which is a consequence of the holders inequality. This is called the Minkowski's inequality, which plays a very crucial role in establishing the structure of the LP spaces as a normal linear space. Now, what does this talk about? It is a generalization of the following relation. If x and y are vectors in R3, then we have that is the length of x plus y length of the length of x plus y is less than or equal to the length of x plus length of y. Or geometrically, this means the following. This is the vector x, this is the vector y. Then, by definition of the addition of vectors, you see that the diagonal represents the vector x plus y. Okay. Now you see that the length of the look at the triangle. So look at the triangle OEC. Then we have the length of OB, that is designated by this, and you have length of OA. This is equal to the length of y, then length of OA, the length of x, which is also equal to, being this OABC we get parallelogram, this is also equal to length of BC. And you know that from triangular inequality, length of OC is less than or equal to length of OB plus length of EC, which is equal to so this is we have this relation that length of x plus y so this is a triangular inequality that you have valid in a vector space where you have introduced the concept of length. In fact, this turns out to be a basic property that you require when you define length. And suppose you have a vector space and there is a norm defined, and the norm, we would like the norm to satisfy the so-called triangular inequality. And that is exactly what you observe here in 2. Okay, so Minkowski's inequality is a generalization of the triangular inequality. So that is what it is all about. So as we have seen that the anticipation of such an inequality came from our knowledge of what is called the triangular inequality in vector spaces. I think that introduction is enough, and so if you look at 2, what does this mean? This means possibly you can write suppose this is defined like this, then we should have the following ending. Now you see that we have assumed here that f and g are measurable functions on x with range from 0 to infinity. Now if f and g are measurable functions, then you see that f plus g is a measurable function, and what you have is this modulus or absolute value of f and absolute value of g. These are measurable functions. F measurable implies mod f measurable implies, and therefore mod f has range in the extended half line, namely 0 to infinity. So all the conditions of this are satisfied. So you have mod f, mod of f plus g, mod of f, mod of g. The power p, they all satisfy, these functions satisfy the requirements of what is stated in this theorem. That is why this is proved under the condition that f and g are measurable functions on x with range 0 to infinity. That is no restriction at all. Okay? Because you see that mod f satisfies these things, and eventually when you try to define length, you have to use mod f. So that is just a remark. I mean, that we will talk more about this later when we work with it. Okay. So our task is to prove the Minkowski inequality. Now this follows from an application of the Holder's inequality. How do we apply Holder's inequality? Let me just take this out. So the Holder's inequality is an essential ingredient in the proof of the Minkowski inequality. So let me just take it out. So let me prove this Minkowski inequality. So we call the assumptions f and g are extended non-negative value functions. That is, it could take value plus infinity also at some places. Okay, and they are measurable functions. And then, of course, you have to have some kind of conditions on that, so that the integral f to the power p d mu exists. Okay, and so also integral. Okay, so it doesn't matter even if it becomes infinite, the relations will. So we'll prove this. So we observe the following. Note that f plus g p, you know the condition of p 1 less than p less than infinity, and this is equal to f plus g p minus 1. Now apply Holder's on this. So we have integral this is less than or equal to f to the power p one by p, where 1 by p plus equal to 1. A similar holds for so you have estimates for both these terms, namely this term as well as this, right? So you call this 1, this 3 you call this you call 4, and you have an analogous statement for this one. Okay. Now note that that follows from this relation, it's 1 by p plus 1 by q equal to 1. Okay, this is essentially 1 by p plus 1 by q equal to 1. So you get pq equal to p plus q, and from that you. So that implies to the power 1 by 1 minus 1 by 1 minus 1 by q is 1 by p. Okay, because 1 by p plus 1 by q, this is less than or equal to integral over x I think I have skipped one step possibly. So I will. This is equal. That's fine. So we. Therefore, integral f plus g p is less than or equal to integral over 1 by q, and use this inequality times integral 1 by p. Okay, so that would follow from this inequalities applied and then worked on that. So you work with this and then you have the two inequalities that you have, combine them together. This is what you, okay. Use the fact that p minus 1 times q equal to. So that implies this is actually using 3 and 4. Okay. Here you have used 3 and 4. And that in turn implies yeah, this in turn implies integral over x f plus g to the power p that means you are taking to the power 1 by p because you have 1 by p plus 1 by q equal to 1. This is less than or equal to integral 1 by p because you are using 1 minus 1 by q 1 by p. Provided, of course, provided so that is of course taken care of because we are assuming both f and p are non-negative extended real valued functions. Okay. And of course the and the RHS that means these two are less than. Okay. So from this, and now it is quite easy to see 1 by p plus 1 minus 1 by q equal to 1 by p. Therefore, So this is Minkowski's inequality. So that completes the. It's quite simple. It's an application of the holders give you the ingredients to establish the Minkowski inequality. It's quite easy to work. Now, note that t to the power p is a convex function for the assumed p. Now this implies f plus g divided by 2 is less than or equal to so if f and g are so if integral fp is finite and integral gp is finite, then it clearly follows that integral f plus g to the power p is finite. Finite. So this follows from this inequality. Okay. Therefore, the condition that we have said is the RHS is less than infinity is taken care of. And now this is an important relation that is required while proving that norm of f plus g. So as I said, this type of relation where norm of f defined as integral of x And this is crucial in proving that two things. One, f plus g is an LP function whenever f and g are LP, and the norm of f plus g is bounded by norm of f plus norm of g, which is essentially the generalization of the triangular union. This is what we wanted. Now, therefore, that completes the proof of this result, and we ask the following question. Namely, Holders and Minkowski. Okay. Now, when does equality hold in the case of the see, you have this, we have this result in the this is the Holder signal. Okay. So, when do you have equality holding good? This is the question that you ask, right? And the answer to this turns out to be that when f and g are okay, so we will discuss this equality problem probably in the next lecture. So, thank you very much. So, let me wind it up at this stage.